A phase diagram, like this one pictured here, is a diagram that shows how the states of matter in a system are affected by changes in temperature and pressure. This phase diagram is for water, and again, a phase diagram shows how the states of matter are affected by changes in temperature and pressure. So as we look at a phase diagram, you will notice that our two variables are temperature and pressure. Temperature in degrees Celsius is along the x-axis. Pressure in kilopascals is along the y-axis. We have several different things that we can determine based on the phase diagram. A couple things to note right now is that this seemingly random number is actually our standard pressure. If you remember from the last lesson, standard pressure is 101.325. So standard pressure is going to be important when we look at the melting point and the boiling point. And the three different colors that are represented on this phase diagram are the different states of matter: solid, liquid, and then vapor. And we will look at some of the other parts down below. But we can have a phase diagram for any pure substance. We have water here, and down below we have one for hydrogen down below. So some vocabulary words that we need to know for this section is liquefaction. It's the first one. Liquefaction is a conversion of the gas or a vapor into a liquid. In order for this to happen, the gas must be below a certain temperature and at a specific pressure. The temperature and the pressure needed to liquefy a gas changes when we talk about different gases. So in order for us to liquefy that gas, we have to cool it off and increase the pressure. The increased pressure is going to force the particles to move closer together. And decreasing the temperature is going to slow the particles down. So they get slower and closer together, which is why they condense. We use phase diagrams to determine that temperature and pressure needed to liquefy a gas, which is, again, the process of liquefaction. Some pieces of data that we're going to pull off a phase diagram are these next three words: critical temperature, critical pressure, and then the triple point. So here are the definitions of these words. Critical temperature is essentially the maximum temperature at which a liquid can exist. Again, these are dependent on the type of gas. So for hydrogen, it will be different than it is from nitrogen, than it is from carbon dioxide. It's not a set critical temperature for all things. It's per type of molecule. So for every gas, there's a temperature above which no amount of pressure will result in liquefying that gas, and that is known as the critical temperature. Critical pressure is the pressure needed to liquefy the gas at the critical temperature. The critical temperature of a gas is an indication of the strength of the attractive forces between the atoms or molecules. The critical pressure of that gas depends on the critical temperature. And again, when we look at a phase diagram, we will see how those two are connected. The triple point is another piece of data that we can pull off of a phase diagram. The triple point is the specific temperature and pressure at which all three phases of matter exist at equilibrium. Temperature and pressure at which all three states of matter, solid, liquid, and gas, exist in equilibrium. Triple point. Okay, I feel like the best way to know what all these things mean is to really analyze a phase diagram. So we're going to start with the phase diagram of water, which is pictured here. It's the same one that's up above, and we're going to answer these questions. I'm going to start with the ones down here, just seeing if we can simply read that diagram. So determine the state of matter that exists at 50 degrees Celsius and 0.1 kilopascals. So we are going to 50 degrees, which is somewhere in here, and 0.1 kilopascals, our scale. It's very, very tiny, somewhere right there. Again, we don't have to be too exact. We're only after the state of matter, which means we are clearly in the vapor, which you could also referred to as the gaseous phase. Negative 30 degrees Celsius and 50 kilopascals. So negative 30 somewhere in here, and 50 kilopascals would be in this region. So again, we are in the solid state of matter. 105 degrees Celsius and 1,000 kilopascals. 105 and 1,000. Somewhere up there, I'm going to go ahead and say we are in the liquid phase. And the last one, 30 degrees and 100 kilopascals. So 30 degrees and 100 is going to be just below there. So liquid again. All right. Again, that is kind of some basic reading the diagram. Here, this next portion is using the vocabulary from up above. So the critical temperature of water. Critical temperature is, again, the maximum temperature at which a liquid can exist. So the critical temperature here is going to be this spot where we are transitioning from our solid line to the dotted line. That's our critical temperature. This diagram helps us out because they have it labeled for us. The critical temperature is 374 degrees Celsius. The critical pressure then depends on the critical temperature. So when we are at 374 degrees Celsius, what is that pressure? So we go across to pressure. The critical pressure is 22,100 kilopascals. The triple point temperature, again, this phase diagram has triple point labeled for us right here, but on any phase diagram, it's going to be that point where we have solid, liquid, and the gas all bordering. They all share that one point in common. So the triple point temperature for water is 0.01 degrees Celsius. The triple point pressure then is from the y-axis, 0.611 kilopascals. The normal melting point, again, the word normal and this one implies we are going to pull that data from standard atmospheric pressure, which is, of course, 101.325, which is why our phase diagram has a dotted line all the way across at that standard pressure, this dotted line right there. So melting point, melting again is the transition from solid to liquid. So our melting point is this right here. Again, we are at standard pressure. The melting point is 0. Maybe you recognize that already because we are talking about water. And then the normal boiling point, so we want to stay on that standard pressure line. Normal boiling point, no surprise here, is 100 degrees Celsius. So again, that's the types of questions that we will be asked with phase diagrams. I have included the phase diagram for hydrogen down below. the side label over here got cut off, but it is pressure in kilopascals. This phase diagram is not as friendly as the one up above because they did not give us standard atmospheric pressure. I mean, it's on here, but it's just not labeled as obviously as the one up above. So again, standard atmospheric pressure, 101.325 is going to be right there. And the temperature is in Kelvin, is still down along the bottom. So I am going to leave these blank, but I want you to finish these on your own, doing the same process that we did up above. You're just going to read the phase diagram and answer those 6 questions. Find those 6 pieces of data. So I will leave those blank, but I do want you to fill them in. Let's see if you can read a phase diagram.